Hey there, fabulous students. Well, so today we're going to take a look at logs. But before we do, let's have some bell work. Oh, and this is going to be assignment 66. But for bell work today, would you do me a favor and please graph y equals 3 to the 2x minus 1 plus 4. Okay? Use your reference points, use your transformations. Come back when you're done. Hey, welcome back. So hopefully you started off with your reference points, negative 1, 1 over 3, 0, 1, and 1, 3. That's what this is giving. That's what the exponential gives. It gives the reference points. It gives the fact that we normally have a horizontal asymptote at y equals 0, and it gives the shape. Because this number is bigger than 1, we know we're dealing with exponential growth. Okay? So let's apply our transformations. I see this plus 4, it's outside the function. And so we know that this plus 4 affects all the y values, including this y value. But what about x transformations? I see 2 of them. I see this minus 1, and I see this times 2. Since inside is opposite land and I'm doing SATMEP here, I'm going to have to add 1 to all the x's. That's not an x, so I don't have to do anything there. So my intermediate points will be 0, 4 and 1/3, 1, 5, and 2, 7. Don't forget over here we have y equals 4 for our horizontal asymptote. Finally, I have to come back and divide all the x's by 2 to take care of that horizontal compression. So my final points, the ones that I'm going to be graphing, 0, 4 and 1/3, 1/2, 5, 1, 7. So we have our horizontal asymptote. Please make sure you always label that. And then 3 points for our exponential growth function. I find it easier to draw the curve and then label the points on the curve, having drawn a nice smooth curve. And 1, 7. Ta-da! There's our graph. Okay, I hope that was comfortable for you. If not, please seek me out or practice more on your own. Now, the second thing I want to ask you is, I'm going to give you some functions, and I'm going to ask you what they have in common. Okay? All right. Yeah, I really want to do that, except that I'm seeing this note to myself over here that says we should do one more graphing thing first. But it's not a graphing thing. It's a transformations thing. Okay, so we know the reference graph here is y equals 7 to the x. And we know that that's exponential growth. But I see 3 transformations here. Maybe 4 if you see these as 2 different ones. So I would really like if you took a minute to explain how these transformations affect this reference graph. Okay? So take a minute to think about that. Try and give me a nice complete answer. Hey, welcome back. Did you say that we have 2 y transformations, one that shifts the function down 4 places, and what does this do? Well, the 2 is a vertical stretch, and the minus is a reflection across that x-axis. We're going to multiply all the y's by negative 2. Negative will flip the graph upside down, and 2 will stretch that graph a bit. What about this plus 3? Does that go to the right? No. Inside is opposite land. This graph moves right 3. Okay, and finally down 4. Good. So why don't we graph it just to get a little more practice with that? Pause the video, give it a go. 1, 1 over 7, 0, 1, 1, 7, y equals 0, our horizontal asymptote. So the first thing I'm going to do is multiply all the y's by -2 times -2 times -2 times -2 times -2. So I end up with -1. Ooh, I guess I could do that transformation now at the same time, couldn't I? Sure, let's take care of that. Let's subtract 3 from all the x's. So now I've got -4, -2 sevenths, -3, -2, and -2, -14. Y equals 0 is still our horizontal asymptote. Okay. So as x heads closer and closer to 0, the y values of the function are going down, down, down. And that's kind of in line with what I expected. I expected an exponential growth that I flipped upside down, and so now the shape would look like that. But I still have this one transformation left to do, so I need to come back and subtract 4 from all the y values. That's a 4. There we go. So what am I going to be left with? -4, -4 and 2 sevenths, -3, -6, -2, -18. And over here our horizontal asymptote is at y equals -4. Okay. And horizontal asymptote at -4. Kind of wish I had the top of the board. Y equals -4. There's my graph. There's -4, -4 and 2 sevenths. There's -3, -6. And then I have -2, -18. Clearly not drawn to scale, but I get a quick understanding of what's happening here without having to fumble for a calculator. All right, so with that in mind, tell me, what do these pairs of functions have in common? Okay, our first pair, y equals f equals x minus 3, and g equals x plus 3. That's one pair. Here's another pair. F equals cube root of x, g equals x to the third. What do these pairs of functions have in common? I know over here you're saying, well, they're both linear, or they have the same slope. But here, no, that's not true. So what do you know? Well, I wonder what happens if I do f of g of x. So I'm going to take g of x and plunk it in there. I'm going to have x plus 3 minus 3. X plus 3 minus 3 is x. Hey, we saw that recently, didn't we? I wonder what g of f of x will yield. So now I'm going to take f of x, and then I'm going to plug it in there. And so I get x minus 3 plus 3, which is x. What did we say it meant when you did the composition either way and you got x each time? That's right. These pairs of functions are inverses of each other. I mean, I can see this one graphically. These are just our reference graphs. There, there. And we know we pass through -1, -1, 0, 0, and 1, 1. There's y equals x to the third in black. And if we look at cube root of x, y equals cube root of x passes through those same points with a different shape. In fact, I see the reflection across y equals x. I know these are inverses of each other. Yeah, these are inverses of each other. So I want to say something about inverses, which is You know how yesterday or in the last video we looked at y equals b to the x? And we had as its reference points, pause the video, write down the reference points. Come back in a minute. Or just say them out loud to yourself. Did you say negative 1, 1 over b, 0, 1, 1, b, and y equals 0, the horizontal asymptote? In fact, I want to write horizontal asymptote, y equals 0. Yeah, nice, good. Now, what's the inverse of this function going to look like? That's what I want to ask now. What's the inverse of this look like? Well, remember 2 videos ago? Switch the ordered pairs. So if I switch the ordered pairs here, I'm going to have 1 over b, negative 1. I'm going to have 1, 0. And I'm going to have b, 1. Ooh, and because I'm switching x's and y's, this now becomes x equals 0, which is no longer a horizontal asymptote. This is now going to be a vertical asymptote. So this thing that is the inverse of this exponential, and I know the exponential has an inverse because, well, it passes the horizontal line test. So I can switch the x's and y's and get these points. But I'm wondering what function we're talking about. Because if I switch x's and y's, I don't know how to solve that equation quite yet. I mean, some of you may remember from Algebra 2, but we certainly haven't talked about solving this in pre-cal yet. And we're almost there. We're just about at that point. In fact, yes, I have that. Yeah, I think I kind of need to now define this function. What function is it that passes through these points and has this vertical asymptote? Well, the function that is the inverse of an exponential is y equals log base b of x. This is the inverse of this. Log is an inverse of an exponential. And in fact, our definition is log base b of n equals p if and only if b to the p equals n. B to the p equals n. That's how I'm understanding this. That this is the base, this is the power, and that's the answer, right? That's what we see here. Base, power, answer. Okay, more on that later. I do want to do some graphing with you. Yeah, I do want to do some graphing with you with logs now. So now that we have this understanding that a log is an inverse of an exponential, and we have some reference points to work with, why don't we try graphing this? Y equals log base 3 of x. Just that. Just that. What's that going to look like? Well, notice the base is 3. And remember, our reference points for log base b of x, the reference points we had for this were 1 over b negative 1, 1, 0, b 1, and x equals 0, a vertical asymptote. Okay? So our base is 3, which means I'm going to replace these b's with 3's. So our graph, 1/3, negative 1, 1, 0, 3, 1. X equals 0 for a vertical asymptote. Okay. Boop, 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 boop. And so I have 1/3, negative 1, 1, 0, 3, 1, and a vertical asymptote over here at x equals 0. So if I'm asked about the domain and range, well, I see my domain starts here and goes over. So the domain is normally 0 to infinity. The range, on the other hand, well, that's going down forever, and that's actually going up forever. I'm going to say negative infinity to infinity. That's for my log function. Now, if we think back to our exponential, y equals b to the x, and its shape, it had a domain of negative infinity to infinity, and it had a range that went from here up. Didn't include this because this was a horizontal asymptote, so we had 0 to infinity. Notice further confirmation that we're looking at things that are inverses of each other. The domain here is the range here. The range here is the domain here. So flip, flip, and that's what we get for our log. Our log has a domain that goes from 0 to infinity. Our log has a vertical asymptote, as opposed to the exponential, which has a horizontal asymptote. Okay? So what about this one, y equals ln of x? Well, this one actually comes from the French. This is logarithmique naturale, and it's log base e of x. And so my reference points are going to be 1 over e, negative 1, 1, 0, e, 1. And of course, x equals 0, a vertical asymptote. The shape is the same. Just because we give it a French name doesn't mean it ceases to exist. 1, 0, or changes to be a completely different function. 1 over e, negative 1. And x equals 0, the vertical asymptote. Instead, what I would say is people adopted this over this because it was less writing. And it's more fun to say logarithmic natural. Good. So now we need to talk about applying transformations here. So when I look at something like log base 3 of x minus 1 plus 2, I'm going to start with my reference points, 1 over 3, negative 1, 1, 0, 3, 1. Where am I getting the 3's from? That's the base. I see an outside transformation and an inside transformation. Inside is still opposite land. I'm still going to add 1 to all the x's. Outside is still normal land. It still affects y values. I'm adding 2 to all the y values. So I've got 4/3, 1. I've got 2, 2. And I've got 4, 3. And of course, x equals 1 is our vertical asymptote. So here's my graph. Why is it there? It should be here. That x, oh no, it shouldn't. Okay, let's try again. X equals 1 for the vertical asymptote. Characteristic shape, 4/3, 1, 2, 2, and 4, 3. Okie doke. All right, how about 1 or 2 more of those? Can you graph for me y equals log base 2 of 3x plus 4? Give that one a try. Hey, welcome back. What were your reference points? Did you have 1 over 2, negative 1, 1, 0, 2, 1, and x equals 0 for a vertical asymptote? Because that's what I got. Inside is opposite land. I'm not going to multiply all the x's by 3. I'm going to divide all the x's by 3. And here, outside is normal land. I see plus 4. I do plus 4 to all the y values. Now, what about this? Well, I was supposed to divide by 3 here. But that doesn't really change the value of our vertical asymptote. And here, some people get upset with this. Remember that this is the same as 1/2 divided by 3 over 1. And as Mrs. Rowan taught me, flip and multiply that second term to get 1/6. So you may be happier with this as being 1/6, comma, 3. And then here we have 1/3, comma, 4, and 2/3, comma, 5. So my graph still has a vertical asymptote here at x equals 0, still has that characteristic shape. These y values are all positive, so I'm just going to put them here. 1/6, 3, 1/3, 4, and 2/3, 5. Ta-da! All right, this compresses horizontally our reference graph by a factor of 3, and this shifts our graph up 4 places, which is why these y values are bigger than we're accustomed to be. All right, so what can you do with this one? Y equals 2 log base 3 of 4x plus 5 minus 1. All right, so that's as bad as it gets on our CFA. Will you please use your transformations to graph this? So reference points, 1/3, -1, 1, 0, 3, 1. Really, don't forget this, because if you forget this now, you're going to forget it later as well. At least this has been my experience. 2 y transformations, 2 x transformations. Let's do one of each. So I'm going to multiply the y's by 2. That's an x, so I don't touch it until I come back and do inside is opposite land and subtract 5 from all the x's. So where are my intermediate points? Well, -15/3 plus 1/3 is -14/3, and here we have -2. Now I've got -4, 0, and -2, 2. Of course, over here we have x equals -5 for our, not horizontal asymptote. We're not doing an exponential. We're doing a vertical asymptote. And so our vertical asymptote is going to be x equals -5. Well, maybe, maybe not. Let's see if that bears out. I subtracted 5 from all the x's. Yes. Okay. Next, I'm going to come back and divide all the x's by 4. And I'm going to subtract 1 from all the y's. Look, I gotta divide that by 4 too. Come on. And that's one of the reasons why I started here. I'm doing the transformations not just to the reference points, but to this as well. Not only am I more likely to get the correct vertical asymptote, because I'm doing it at the same time, I'm likely to, in fact, be continually reminded that I need to be thinking about that vertical asymptote. So I'm going to have -14/12, which is -7/6, -3, -1, -1, -1/2, 1. And of course, x equals -5/4 for our vertical asymptote. So here's -5/4. And our graph still has that characteristic shape. Here I am, -1/2, 1. And then here, -1, -1. And then here, even closer to the vertical asymptote, -7/6, -3. So there's my graph. Okay, well, I hope you're feeling pretty comfortable and confident with this. If not, you should definitely let me know. And oh, by the way, we really do expect you to be able to graph this. Remember, this is log base e. ln is log base e of x. So my reference points are 1/e, -1, 1, 0, e, 1. You can always decimalize these if it's a calculator active problem. I know I need to multiply the y's by 2, and I need to add 1 to the x's. Don't forget, x equals 0, the vertical asymptote, gets a plus 1 also. So I have 1 plus 1 over e. I have negative 2, 2, 0, and e plus 1, 2. X equals 1 for a vertical asymptote. My graph then, with a vertical asymptote at 1, same characteristic shape, 2, 2, 0. And this one must be e plus 1 comma 2. And this one over here must be 1 plus 1 over e negative 2. Okay? Yes, I do need to know exponentials and logs. I need to be able to graph them, and I need to be able to graph a very specific log called ln of x. All right, so that's the graphing stuff done. Now, let's take a look at this. Log base b of n equals p. Now, remember, this was going to be true if b to the p equals n. So these are the things that are inverses of each other. And there's this thing, there's this way of rewriting a log to be an exponential. And there's a number of ways I can show you to do it. One is one that I really quite like from Mr. Cleese, which is he thinks about this as scorpion tail. Base, power, answer. And so he says the base is b, the power is p, and this stuff in here, inside the log, that's our answer. Okay? And in fact, some of our problems ask us to actually consider rewriting an exponential as a log or a log as an exponential. So for example, if I have 10 squared equals 100, this is an exponential expression, c, the exponential power. But now if I want to write this as a log, that's my base, that's my power, that's my answer. Base, power, answer. And so written as a log, I'd have log base 10, base, power, answer. And so we get log base 10 of 100 is 2. Now, remember, log base 10, it's pretty common. In fact, this is called the common log. I think ln is even more common, but this one was named as the common log. And so often, you won't see anything there. You'll just see log. Log means log base 10. Okay? Okay. So, what are we going to do? Well, can we rewrite this exponential expression, 3 to the 2 equals 9, as a log expression? Like we did with this last problem, can you rewrite this exponential expression as a log expression? Did you do it? How about now? Base, power, answer. Base, power, answer. So I'm going to have log base 3 of 9 equals 2. Base, power, answer. Base, power, answer. Okay. All right, how about this one? Log base 3 of x equals 2. Can you rewrite this log as an exponential? Base, power, answer. 3 to the second equals x. Okay? And we should be able to go both ways. I should be able to give you 2 to the negative 3 equals 1/8, and you should be able to turn this exponential expression into a log expression. Log base 2 of 1/8 is negative 3. Base, power, answer. Base, power, answer. But you should also be able to go from being given a log n equals q. And you should be able to turn this log into an exponential expression. So what's my base here? That's right. The base here is 10 because this is common log. There's no number, no base here. Therefore, our base is 10. So where do we go from there? Base, power, answer. 10 to the q equals n. All right? Let me know if you have questions about that. You can certainly feel free to 3 of 27 equals, let's just do 3 to the 3 of 81 and 4. Okay, so scorpion tail, wow, base, power, answer. 3 to the 4th equals 81. All right, now I'd like to sort of use our understanding of the relationship between logs and exponentials. They are inverses of each other. That means like plus and minus, they undo each other. That means like multiply and divide, they undo each other. Taking the log of an exponential or exponentiating a log, these are inverses and undo each other. And we'll see more of that shortly. Okay, solve, is that what I'm up to? No, here we go. So log base 2 of 8 equals 3. Would you please rewrite this as an exponential expression? 5, 4, 3, 2, 1. Base, power, answer. 2 to the 3rd equals 8. Done. How about this one? Log of 1,000 equals 3. Yeah, I want you to rewrite this as an exponential. So, what's my base? Well, common log, the base is 10. Power, answer. 10 raised to this power is that. Okay, how about this one? Log base, sorry, the next one's an ln. ln of 10 equals 2.3076. Will you please rewrite this log expression as an exponential? The log base here is e. E to the power equals answer. Okay? Base, power, answer. Nice. All right. So we've rewritten logs as exponentials. And I think we're comfortable rewriting exponentials as logs, but let's just confirm that. 3 to the 5th equals 243. Will you please rewrite this exponential expression as a log expression? Rewrite as a log expression. Okay, base, power, answer. Log base 3 of 243 equals 5. Nice, 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 nice. And what about this one? C to the P equals D. Can you please rewrite that as a log expression? Did you say log base C of D equals P? Base, power, answer. Base, power, answer. Okay, so I think now that we've sort of gone back and forth, writing logs as exponentials and exponentials as logs, I feel confident about moving on to solve. So, solving. Log base 6 of x equals 2. Wow, we're asked to solve this equation. And there's a couple of ways we can do it. Based on what we've just been doing, the book would really like us to do scorpion tail. They'd really like us to rewrite this log expression as an exponential expression, base, power, answer. And so we know that 36 equals x. Ta-da! That's it. That's all I had to do to solve, was to get x by itself, and rewriting that log as an exponential took care of that. Now, speaking of which, I don't know if you heard me say it a few minutes ago, but remember logs and exponentials are inverses, and because they're inverses, like adding and subtracting, or multiply and divide, because they're inverses, they undo each other. So if I want to undo this log, I need to exponentiate. No, really, it's a verb. Exponentiate both sides of the equation. And what am I using to exponentiate with? Well, I'm using the log base, because 6 raised to the power of and log base 6 of, these are the things that are inverses and cancel each other out. So on the left-hand side, we just have x, and on the right-hand side, my base is 6, my power is 2, and that's the same 36 we got over here. Okay? So whether you're scorpion tailing it or exponentiating, you can still get to the same answer. I will say, as the solving problems get harder, I reach less often for scorpion tail and much more often for exponentiating. I think scorpion tail is this fabulous, great thing to be comfortable with as a way of transitioning out of exponential land and into log land. But in a couple of videos, we'll be whimpering if all we can do is scorpion tail. So let's do some more of these solving problems. How about log base 7 of 1 over 49 equals y? Okay, so I'm asked to solve this. What can I do here? Well, you know, I kind of feel like, I don't want to say y there. I kind of feel like I want to say question mark. What is this expression equal to? What is the value of this expression? I guess that's why I'm saying solve. Well, I'm going to do scorpion tail here and say 7 to the question mark equals 1 over 49. Funny thing about 1 over 49, it's 1 over 7 squared, or 7 to the negative 2, which means this is equal to that. 7 to the question mark equals 7 to the negative 2. And now our book says, well, we've got this really, really interesting property that says if these terms are equal and the bases are the same, then the powers must be the same. And so question mark equals negative 2. So this expression, since that's what question mark is, this is equal to negative 2. You may not be comfortable with that, or you may be very, very comfortable with that. The bases are the same and the terms are equal. These have to be the same as well. But I think I could also understand this problem a different way. Let's see what happens. We don't know what that is. I don't want to show you that other way yet. Nope, sorry, take it back. I want to get to log properties another day, and I'm not bringing them up now. But there's another way with log properties. Okay. Please rewrite this log as an exponential so that you can simplify, not solve, just simplify here. We want to simplify this expression. And I don't know what that is. That's what I'm trying to find out. So we have a couple of ways of doing this, but we're encouraged at this point to think about scorpion tail. 3 to the question mark equals 81. Base, power, answer. Well, curiously, as we said earlier this year, 81 is 3 to the 4th. When the bases are the same and the terms are equal, what must be true about the powers? Powers are also equal. So then I know question mark is 4. Here's question mark. What is question mark equal to? 4. Base, power, answer. Yes, 3 to the 4th is 81. Okay. How about log base 8 of 8 to the 4th? What can you do to simplify this expression? Well, you can always scorpion tail it. 8 to the question mark, 8 to the 4th. Since the bases are the same and the terms are equal, I know the question mark is 4. I know that this expression equals 4. Okay. I kind of want to bring up this other idea, though. What was the relationship between logs and exponentials? That's right, they're inverses of each other. And inverses undo each other. Multiply undoes divide, subtract undoes add, and look what I've got here. Log base 8 of 8 to the power of. When these are the same, I can just cancel them. And I'm left with that power. Okay? Log base 8, 8 to the power of, these are inverse operations. It's not unlike saying 8 divided by 8. And then times 8. There we go. So, simplify. I like that better than solve for those last problems. How about log 10 log 10 yeah, that's it, just log 10. What's that simplified to? Well, what's my log base here? Well, right, 10. So if I rewrite this as an exponential, 10 to the question mark equals 10. And so I know the question mark is 1. I could get to the same place by saying log base 10 of 10 to the 1, these cancel, and I'm left with that 1. All right? How about this one? ln of e to the 15th. Remember, this expression can be written as log base e of e to the 15th. And again, I think there's some options for us if we're trying to figure out what this expression is equal to. Here I can do scorpion tail. And since the bases are the same and the terms are equal, we know that the powers also have to be the same. So this expression is equal to 15. But really, there is this other way. Log base e, e raised to the power of, undo each other because they're inverses, and I'm left with 15. Okay? All right. I think the last thing I want to talk about in assignment 66 are some things that we should know. These really need to be deeply and comfortably memorized. Log base a of 1 equals, well, let's say we don't know. And let's scorpion tail it. A to the question mark equals 1. What power does that have to be? So when I do a to that power, I get the answer 1. When is 1 the answer in an exponential expression? That's right. 0. a to the 0 equals 1, provided a doesn't equal 0, because 0 to the 0 is not always 1. You don't have to worry about this, but you'll probably see this if this is our question. Okay, log base a of 1. Now, let's think about this from a graphical point of view. Log base a, so I know that this point is 1 over a, negative 1. This is 1, 0, and this is a, 1. Now this says, what's the value of the log at x equals 1? Here's x equals 1. What's the value of log at x equals 1? 0. There it is. So I can be thinking about this graphically as well. How about log base a of a? What's that equal? Again, I know that it is 3 different ways. One of them that you might be comfortable with is scorpion tail. And then to say if the bases are the same and the terms are equal, the powers need to be the same. So this equals 1. If I think about this question graphically, here's my log graph. Here's my vertical asymptote at x equals 0. That's 1 over a negative 1, 1, 0, a, 1. Now what does this say? On this log graph, when the input is a, what's the output? Well, here the input is a, and the output is 1. Log base a of a is always 1. Log base a of a is always 1. So if I see log base 2 of 2, well, that's going to be 1. And log base 3 of 3, that's going to be 1. And ln of e, because that's the same as log base e of e, that's going to be 1. Okay, so please make sure you know and understand this. We've certainly seen it on our graphs. We can form it by rewriting as an exponential. But I would say these are things that just need to be memorized, like log base a of a to the x. What's that equal to? Well, again, if I rewrite this as an exponential, base, power, answer, if the bases are the same and the terms are equal, the powers have to be the same. So question mark equals x. This is x. And likewise, if I'm not scorpion tailing it, what about thinking that log base a and a to the power of, these are inverses, and they're going to cancel each other out. Now, I know that you see that now, but 3 or 4 days from now, you might be forgetting unless you take these last, 6 problems that we're doing and really memorize them. I mean, I need you to be able to see log base 4 of 4 to the third is 3. And I don't really care how you know that's 3, but I'd like you to know it's 3 that fast. And the way I'm thinking about it is log base 4 of 4 to the power of, those are inverses, and I'm left with this. Okay? All right, so how about this one? A to the log base a of x equals what? Well, that's not a log. So I can't rewrite that as an exponential. It already is an exponential. I could think about rewriting this, but I can't connect it to that. So here's what I recommend. This is a to the power of, and this is log base a. What do we know about logs and exponentials? They're inverses. They undo each other. So this is equal to x. When I see a raised to the log base a of x, that's just equal to x, because these are going to cancel. All right, and the last one. This is sort of a proto-solving question. log base a of x equals log base a of y. And we're asked to consider simplifying this or solving this, but I think it's really simplified. And the way I'm going to go about doing it is to get rid of the logs on both sides. They're both log base a. And so if I want to get rid of the log, I need to exponentiate. I need to exponentiate here with the log base. The log base is a, so I'm going to do a to the power of on both sides. And when I do a to the power of on both sides, a to the power of log base a, they're inverses. They cancel. A to the power of log base a, they're inverses, and they cancel. And so I get x equals y here. Okie doke. Nice. Okay. I think we'll call it there. And then we'll take on some more rewriting and solving in the next video. Have a wonderful day, everyone. I'll see you in the next video.